Physical quantities are divided into two categories. Those quantities having magnitude only and no direction are called scalar quantities. Example of scalars are mass, volume, density, work, speed, temperature, etc. Those quantities which have both magnitude and direction is called vector. Example of vectors are displacement, velocity, acceleration, force, momentum, weight, etc. Representation of vector. A vector is normally represented in two-dimensional real coordinate space that is nothing but a plane, or three-dimensional real coordinate space which is a three-dimensional space. These real coordinate spaces will be written like this, which is the short form of real coordinate space of n dimensions. Thus, this one is two-dimensional real coordinate space and this one is three-dimensional real coordinate space. And I'll represent the vectors in this three-dimensional coordinate space throughout the tutorial on vectors. Higher dimensions are better if we say variables are also possible. A vector is drawn in three-dimensional real coordinate space by drawing a line, or better if we say by joining 2 points, as we have joined 2 points A and B over here. Out of these 2 points, one is called the initial point and other is called the terminal point. An arrowhead is placed within the line pointing from the initial to the terminal point. The vector is written as AB with an arrow just over it. The initial point is always written first. It may also be written by a small letter like this. The magnitude of the vector is written as modulus sign like this. Position vector. Position vectors are vectors whose initial point is a fixed point which is normally taken as the origin with coordinates 0, 0, 0 in three-dimensional real coordinate space. The fixed point may be thought of as any other point other than the origin. In that case, we get the position vector with respect to that point. In practice, position vector of a point P means that P is the terminal point of the position vector with respect to some fixed point. Any vector AB is always equal to the position vector of B minus position vector of A, which is equal to position vector of terminal point minus position vector of initial point. Direction cosines. Direction cosines of a vector are the cosine of the angles that the vector makes with the positive direction of x-axis, y-axis and z-axis and is normally represented as LMN. Let there be a vector AB in three-dimensional space where the coordinates of AB is like this. Now we have to draw a cuboid making AB as the diagonal of the cuboid and faces AFED and GHCB parallel to XZ plane, faces FGBE and AHCD parallel to YZ plane, and faces EDCB and FAHG parallel to the XY plane. Now bring triangle AFB outside like this. Since AF is parallel to x-axis, therefore if angle BAF is equal to alpha, then alpha is the angle which vector AB is making with the x-axis. Clearly AF is equal to x2 minus x1 and cos alpha equal to x2 minus x1 divided by mod AB. Similarly, if we bring triangle AHB outside, then angle BAH is equal to beta, which is the angle that vector AB make with y-axis. Here AH is y2 minus y1 and cos beta is equal to y2 minus y1 divided by mod AB. We also bring out the triangle ADB outside, then angle BAD equal to gamma, which is the angle that vector AB make with z-axis. Here AD is equal to Z2 minus Z1 and cos gamma equal to Z2 minus Z1 by mod AB. Let mod AB equal to R. Then LR equal to x2 minus x1, MR equal to y2 minus y1, and NR equal to z2 minus z1. Or we get this relation. Here L, M, N are the direction cosines of vector AB, and x2 minus x1, y2 minus y1, and z2 minus z1 are the direction ratios of the vector AB. It can be easily proved that L square plus M square plus N square equal to 1. One should keep in mind that direction ratios are not unique for a vector. Direction ratios are, however, any real numbers which are proportional to direction cosines, which are unique for a vector. In fact, we can calculate direction cosines if we know the direction ratios like this. In this tutorial, I will take the difference in coordinates of terminal point and initial point as direction ratios. Unit vectors. A vector whose modulus or magnitude is unity, that is mod A is equal to 1 unit. It is called a unit vector. In unit vectors, a cap is drawn on top instead of an arrow and is read as A cap. The unit vector in the direction of vector A is written as A cap, which is equal to vector A divided by modulus of vector A. Equality of vectors. This vector may be moved anywhere in three-dimensional space like this. Without rotating it or without changing the direction, the vector will remain the same. Here, all these vectors are equal vectors. Equality of vectors depend only on magnitude and direction and are not on the position of the initial and terminal point. Zero vector or null vector. Zero vector or null vector is that vector which has the same initial and terminal point. Therefore, vector AA or vector BB is a null vector. Collinear vectors or parallel vectors. If any two vectors are represented by two lines which are parallel to each other, then they are called parallel vectors. If their direction is the same, then the vectors are called like parallel vectors. If their direction is reverse, then they are called unlike parallel vectors. As you know, a vector may be moved anywhere in space without changing its direction. Therefore, two parallel vectors are also collinear. The condition for collinearity of two vectors A and B is A equal to mu B, where mu is a scalar and belongs to the set of real numbers. For parallel vectors, the direction cosines must be equal. If the vectors are parallel and also have equal magnitude, then their direction ratios will also be equal. Coinitial vectors. Vectors having the same initial point are called coinitial vectors. Coterminous vectors. Coterminous vectors have the same terminal points. Coplanar vectors. Vectors are said to be coplanar if they are parallel to a single plane in space. Negative of a vector. A negative of a vector AB has the same magnitude as that of AB, but the direction will be opposite, or in other words, it will be vector BA. Multiplication of a vector by a scalar. When a vector is multiplied by scalar lambda, where lambda belongs to a set of real numbers, if lambda is equal to 1, then nothing happens. If it is multiplied by -1, then direction reverses but magnitude remain the same. If lambda is not equal to 1 or -1 and is positive, then the magnitude of the vector changes but not the direction. And if lambda is negative, then both magnitude change and the direction reverse. However, after multiplication, we will always get a vector which is parallel to the original vector before multiplication by scalar, be it like parallel or unlike parallel. Now, a vector A can be written as modulus A multiplied by A cap, the unit vector. Vector B is equal to modulus of B multiplied by A cap, the same unit vector, because vectors A and B are parallel and a unit vector in the same direction is constant. Thus, it implies that lambda into mod A equal to mod B. Parallelogram law of vector addition. If two coinitial vectors A and B are represented by two adjacent sides of a parallelogram, then the vector C represented by the diagonal of that parallelogram is the sum of vectors A and B and is co-initial with A and B. Let this be a parallelogram. The position vector of A and B is written like this. The coordinates of A is A1, A2, A3 and coordinates of B is B1, B2, B3. The coordinates of C is C1, C2, C3. Here OA is parallel and equal in magnitude to BC. Therefore, direction ratios of OA is equal to direction ratios of BC. Therefore, we get C1 equal to A1 plus B1, C2 equal to A2 plus B2 and C3 equal to A3 plus B3. Thus, coordinates of C is this. Triangle law of vector addition. Now watch this triangle carefully. This is vector A and this is vector B and this is vector A plus vector B. Thus it follows that if two vectors are represented by two sides of a triangle taken in same order, where same order means that terminal point of the first vector must coincide with the initial point of the second vector, then their sum is represented by the third side of the triangle taken in reverse order, where reverse order means that the third vector's initial point is not coinciding with the terminal point of the second vector. Here AB equal to A, BC equal to B and AC equal to C. Therefore, AB plus BC equal to AC. There is an easy method for remembering this. To find the sum of AB and BC, what we do, we just erase the terminal point B of the first vector and the initial point of the second vector, which is also B. What we get AC, which is actually the sum of AB and BC. From the triangle law of vector addition, we may conclude that three vectors representing the sides of a triangle taken in order will have their sum equal to 0. Properties of vector addition. Commutativity. To prove commutativity, we draw the parallelogram like this. In figure 1, we apply triangle law for triangle ACD. What we get A plus B equal to AD. In figure 2, we apply triangle law for triangle ABD. What we get B plus A equal to AD. This implies that A plus B equal to B plus A. Associativity. In this figure, let AB equal to A, BC equal to B, CD equal to C. In triangle ABC, AC equal to AB plus BC, which is equal to A plus B. In triangle ACD, AD equal to AC plus CD. Therefore, AD equal to A plus B plus C. In triangle BCD, BD equal to BC plus CD, which is equal to B plus C. In triangle ABD, AD equal to AB plus BD. Therefore, AD equal to A plus B plus C. From 1 and 2, we get A plus B plus C equal to A plus B plus C. Existence of additive identity. Here 0 is the null vector, is the additive identity. Proof. Let OA equal to A. Also we know AA is a null vector and OO is also a null vector. Now we add the vectors by omitting the terminal point of the first vector and initial point of the second vector. We get OA. Again we add the vectors by omitting the terminal point of the first vector and the initial point of the second vector. We again get OA. Thus it is proved. Existence of additive inverse. The negative of a vector is the additive inverse such that A plus minus A equal to 0. Proof. A equal to AB. Therefore minus A equal to BA. Now we add them erasing the terminal point of the first vector and the initial point of the second vector. We get AA, which is a null vector. Subtraction of vector. If A and B be two vectors, then subtraction of these two vectors is defined as the sum of vector A and the additive inverse of B, that is A plus minus B, is the subtraction of vectors A and B and may be written as A minus B. ABCD is a parallelogram. Here clearly AB equal to B, CD equal to minus B, AD equal to BC equal to A. By triangle law on triangle ABC, we get A plus B equal to AC. By triangle law on triangle BCD, we get A minus B equal to BD. Thus, geometrically we may interpret that the diagonal AC of a parallelogram represents sum of the vectors represented by adjacent sides of the parallelogram, and the other diagonal BD represent the subtraction of a vector represented by the adjacent sides of the same parallelogram. You may note that if angle between two vectors is acute, that is less than 90 degrees, then mod A plus B is greater than mod A minus B. If two vectors are perpendicular, that is angle between them is 90 degrees, then mod A plus B equal to mod A minus B. If angle between two vectors is obtuse, that is angle between them is greater than 90 degrees, then mod A plus B is less than mod A minus B. Components of vector in 3 dimensions. Let a point P have coordinates x1, y1, z1. Position vector of point P is OP. Here unit vector along x-axis is I cap, along y-axis is j cap, and along z-axis is k cap. Therefore OA equal to x1 I cap, OB is equal to y1 j cap, and OR is equal to z1 k cap. Now OC equal to OA plus OB, or OC equal to x1 I cap plus y1 j cap. Also OP equal to OC plus OR. Therefore OP is equal to x1 I cap plus y1 j cap plus z1 k cap. Here x1 I cap, y1 j cap, and z1 k cap are called the components of vector OP along x-axis, y-axis, and z-axis respectively. Now what will be the components of a vector whose initial point is not the origin? We are talking about vector AB, where A has coordinates x1, y1, z1, and B has coordinates x2, y2, z2. We know that vector AB is equal to position vector of B minus position vector of A. Therefore AB is equal to x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. Thus components of vector AB is x2 minus x1 I cap, y2 minus y1 j cap, and z2 minus z1 k cap, because these three vectors sum is vector AB. Section formula. 1. Internal division. Let AB be the 2 points with position vector A and B respectively, and C be a point dividing AB internally in the ratio m:n. Then position vector of C is given by C equal to mb plus na divided by m plus n. Proof. Here AC by CB equal to m divided by n, or NAC equal to mCB, which implies n vector AC equal to m vector CB, which implies n into position vector of C minus position vector of A, which is equal to m into position vector of B minus position vector of C, which implies m plus n vector C equal to m vector B plus n vector A. Thus we prove that vector C is equal to m vector B plus n vector A divided by m plus n, where C divides AB in the ratio m:n. When C divides AB externally in the ratio m:n, then vector OC or vector C is equal to m vector B minus n vector A divided by m minus n. This also can be proved like this. Collinearity of 3 points. If A, B and C be 3 points having position vectors A, B and C, then they are collinear if and only if there exists three scalars x, y, z such that x plus y plus z equal to 0 and xa plus yb plus zc equal to 0. Proof: ABC are three collinear points if AB and BC are collinear. Now vector AB equal to position vector of B minus position vector of A, and vector BC is equal to position vector of C minus position vector of B. For their collinearity, AB is equal to lambda into BC, or minus 1 into vector A plus 1 plus lambda into vector B plus minus lambda into vector C equal to 0, or xa plus yb plus zc equal to 0, where x, y, z are scalars. Here x plus y plus z equal to 0. Coplanarity of three vectors. Any two vectors A and B be non-collinear, but they are always coplanar. How? Just move vector B such that initial points of the vectors coincide. Now these 3 points will always be coplanar, as we all know that any three arbitrary points in space are always coplanar. Now these vectors are position vectors with respect to this initial point. Let a third point C lie on this plane. Then C is coplanar with A and B. Complete the parallelogram OMCN like this. Here OM equal to x into B and ON is equal to y into vector A, where y and x belong to a set of real numbers. This we get from collinearity of vectors. Then according to the parallelogram law of vector addition, we get C equal to y into vector A plus x into vector B. This is the condition of coplanarity of three vectors.